So welcome everyone. Welcome for the last presentation, which is my presentation. So Tetris and FPGA, it's a hobby project of mine. For the people that do not know, I work for VI Technologies. I'm a CLA, CLED, and a LabVIEW champion. And I had a hobby. Oh, let me start at the beginning. Let me see the next slide. So first, Tetris on FPGA. What are we talking about? I have a video where I can display the game. So this is actually running on pure FPGA code. There is no code running on a real-time target. This is only FPGA code and using digital I/O. This is running on a on a Myrio, which has no display capabilities. So I'm generating the VISA signal using the digital outputs. What you see here is a resolution of 1600 times 1200 at 59 hertz frame rate and 8 colors. And using special techniques, I can get more colors than that, or the illusion of more colors. If you look at the VI Technologies logo, it seems like there are more colors, but we are using a technique here that is called dithering, which basically puts pixels of different colors next to each other, which from a distance seem like another color. The same you can see at the astronaut in the game, which is black and white. There's only two colors that you can see there, but it has the illusion if it has as if it has grayscales colors. So there are 4 players. The players are playing using Atari joysticks. I will tell you more about that later. And basically it's Tetris. So you get a random block. You can rotate it by pressing the joystick button. You can move the block left and right, and you can hard drop it by pressing the joystick up. The block will fall down, and the next block will appear. You get points for the number of lines you clear. If you clear more lines in one go, then you get more points. And the game speeds up according to the number of lines you are clearing. Yeah, and the game supports 4 players. Let me see. Yes, so the whole idea of this started with a YouTube video that was released last year by Ben Eater. And he basically builds a video card using only a breadboard, some ICs, a crystal, and an EEPROM. He uses the EEPROM to store an image, the crystal for the clock, and then the whole ICs to generate the VGA signal. And I saw that video and was instantly inspired to do that on FPGA. If you want to see these videos, you can Google Ben Eater, or you can look in the description of this YouTube channel where I posted the link, or actually it are 2 videos, 2 parts for it. So both videos are linked here. And it's very, very interesting. He actually continues and builds a whole computer, a whole CPU on a breadboard. And this is just one module of it. But after seeing this, I could instantly see how to port this to an LabVIEW FPGA. So this is the hardware that I'm using. You can find everything online. Of course, the Myrio you can get from our favorite hardware vendor. The Atari joystick and the terminal blocks are found in a lot of electronic online stores and only cost a few bucks. And the terminal blocks make everything a lot easier. Also for debugging. If you start soldering, it just makes it harder. The joysticks, so the CX40, are actually 5 switches. So you have 4 directions and you have the button. And if you push the joystick in one direction, you're actually closing a switch. So to connect this to a digital input on your Myrio, you can use this diagram to basically connect it. And if you notice, there is no additional electronics needed. You can directly connect each of the joystick pins do the digital inputs, and you have a direct input value for all of your 5 directions and button of the joystick. So this is what it looks like. My colleague Kunteo was nice enough to 3D print us a case. So what you can see here are the 4 joystick connectors on the other side, and also here you can see that there is no electronic between it. And on the back side, we are using 5 digital outputs to create the VGA or VISA signal. And it's not visible here, but they also directly connected to the terminal block. There is no extra electronics needed. And we'll see that later. So the first game I built, that was last year, is a Snake on FPGA. It's a Snake game. Some of you may have seen this during NI days in Munich. I had a demo where I showcased this game. Again, this is done the same way, using the same VGA technique. But the requirements, the specifications of this game are a little bit lower. I learned a lot implementing this. And from there out, I was challenged to do the Tetris game. You can get the source code for this game when you visit the VI Technologies website, so vitech.nl. Go to the blog and select Snake on FPGA, and you will find a link to GitHub where you can download the source code. But this presentation is about Tetris. So first, more theory about how to generate a VGA signal. It's actually relatively easy. So as you can see on the VGA connector, you have 5 wires that will be directly connected to 5 digital ins of your choice, and you need to connect a few pins through your on your ground. And then you have this horizontal sync and vertical sync line, which let me put on the pointer. Yes, so you have this horizontal sync and vertical sync line. So what's actually happening is with all CRT TVs and monitors, you have a raster line or a scan line. So basically, you're drawing line by line from left to right. And once the line is at the last point of the visible area, this rectangle here, the electron beam will start going back to the first pixel of the second line. And the time needed to make this transition is what you see here. LCD monitors do not theoretically need this, but to have backwards compatibility, they expect a signal which is the same for VGA and CRT monitors. So they will function. So basically what you need to do is get the timing right and output a digital high until the sync pulse needs to be outputted on these wires, then make it low and go high again. And the same for the vertical links. And the timing for these 2 pulses can be found online, of course. So for SVGA signal 800 by 600 at 60 Hertz, which was the display that are generated for Snake, you have this timing. And what's very good about this is it's actually 40 megahertz, and people that worked with a LabVIEW FPGA know that that is the main clock or the basic clock for the FPGA, which means if you implement this in a single cycle timed loop, every cycle of that loop will be updating 1 pixel on the screen. And down here you find the exact timings. So for the horizontal line, 0 till 800 or 799 will be the visible line. Then you get the front pulse, the sync pulse. This is the time that the sync pulse should be 0 or low. And then you go high again, and a whole line takes 165 single cycles exactly. So you don't have to look at this timing. You can just count cycles, which makes it very easy to implement displays. The upgrade to Tetris so going to 1600 times 1200, which is 4 times the resolution, is 162 megahertz. The 2 is a problem, so I just chose 60. That makes the 60 hertz go down to 59 hertz, but I don't think any human will notice that. And LCD monitors will first buffer a whole screen and then update every pixel instantly, so you will not see the scan line or everything. So the Snake game was 800 times 660 hertz, and the Tetris game is 1600 times 1200 at 95 hertz. Okay, so now looking at the specification of the Myrio, if I open the manual and look at the digital I/O, I can see the minimal pulse width is 20 nanoseconds. And if you do the calculation, you will get at a maximum pulse rate of 50 megahertz. But as you could see in the video, it still works at 160 megahertz. So the question is why? And I think that NI guarantees signal quality. So if you would watch a pulse, a digital pulse on an oscilloscope, you would see a block signal. But if you do that at 160 megahertz, it will more likely be like a wave. But luckily, the electronics in displays and monitors and TVs is very mature, is very well developed, and they handle these kinds of signals very well. So I cannot exactly explain how this works, but it works. Another thing is the logic level of the digital outputs is 3.3 volts. But if you look at the output level of the VGA signals, it's from 0 to 0.7, which means I'm way over the maximum voltage that I theoretically could, that I theoretically need to give a monitor. But also this is well protected with the electronics in the monitor. So I had no problems there. But this also means that I can only make 8 colors. So if you have the RGB colors, red can only be 0 or 1. So it can be black or red. And the same is then for green and blue. And you can mix them. So in total, I can make 8 colors. So if you look at the Myrio manual, you will see that the FPGA used in there is a Xilinx Z7010, which is a CPU and an FPGA built in one. And if you look at the Xilinx datasheet, you can see the resources that we have available. So here on the right side, you see the listing from the compile. We have 4,400 slices and about 60 block RAM. The 60 block RAM is why I wanted to show this, because I use block RAM extensively to draw graphics in on the monitor. Because block RAM will store the graphics, I can index the block RAM and then draw the correct colors wherever they want. And if I see, if I look at this FPGA, I have 2.1 megabits of RAM that I can use to draw my graphics. This is actually a relatively small FPGA. The Myrio is out for a few years now. If you have a single board Rio, especially the newer generations and the compact Rios, the newer generations, you have easily 5 to 10 times, if not more, of storage and slices you can use. But let's say I want to draw a full-scale image in 8 colors. So I have 1600 times 1200, that's the amount of pixels, and then I need 3 bits to display the R, the G, and the red, green, and blue. Then I need 5.7 million bits stored into block RAM. So if I wanted to store 1 image in block RAM, I cannot do this because my FPGA block RAM is too small. This is very important because this means I need to do a lot of optimizations in my code. We will go to the code in just a moment, and I will show you what tricks I used to get it working. But basically, the application is built up out of 3 loops. The first loop is the 160 megahertz loop, which is responsible um, of generating the colors for 4 pixels each. No, that's not correct. It is responsible for generating the VESA signal. So each iteration, it will update 1 pixel. The 40 megahertz loop is responsible to tell the 160 megahertz loop which 4 colors it should draw. Because this is a 160 megahertz loop, I only have 6.25 nanoseconds to run my code, and you can not compile a lot. The compiler will not like you, and it will just not compile. So I have a helper loop that's 40 megahertz. I know I need to have logic in here that gives me 4 colors for the next 4 pixels, which will transfer to the 160 megahertz loop. And then I have a normal while loop, which I am running the game logic. So it runs for all 4 players the Tetris game logic. Okay, so I need to switch now to the virtual machine. So let me see. And share. So if everything went right, you will now see a desktop with a project library. Can you guys in chat say if everything is all right, team? Yes, okay, everything's all right. So you see the project library. You can see here is my Myrio. I don't know what it's doing right now. Yes, Myrio. I have the 40 megahertz onboard clock, and I created a derivative clock of 160 megahertz, which is 4 times the 40 megahertz, of course. If I open the main VI, we can see the 4 VIs that I was just talking about. The first one being the VESA's signal loop. And this is what we are using to generate the pixel. So every iteration of this 160 megahertz loop, I will output 1 pixel on the monitor. I'm using a technique called pipelining. I'm using a technique called pipelining, and I have a counter. This is nothing more than a counter. So it counts the 160 pixels that is needed for 1 line, and outputs me an enable when the vertical counter should count. So this is used to determine which pixel I'm actually updating. I'm inserting an extra iteration because I need to do 4 iterations for each one of the 40 megahertz iterations. So I'm putting 1 extra in here, and then I'm outputting the pixel. So again, we have the connectors. We have the 5 digital outputs: red, green, and blue. The horizontal sync and the vertical sync. And I'm using a pixel FIFO to communicate from the 40 megahertz to the 160 megahertz. So this FIFO will receive the 4 colors that need to be displayed from the 40 megahertz loop. And I did some optimization here to get it compiled, because again, this all executes in 6.25 nanoseconds. But in the first iteration, I get the 3 pixels, or the 3 pixel value. Sorry, I get the RGB colors for the pixel that I'm updated, so the RGB. The second iteration, I get second 3, etc., etc., and that way I have 4 pixels that I displayed on the screen. I have to make sure that I'm outputting in the visual area. So I have 0 to 1599 horizontal and 0 to 1199 vertical. And I'm using this to make absolutely sure that I'm not updating pixels in the time that that the electromagnet or the electrocannon is going from the right side of the screen to the left side. Because if you're using a CRT monitor, you will actually damage it, because you're now shooting electrons where you don't want to have them. And LCD monitors, I find, have a security mechanism where the screen just goes blank. So I put here this AND security gates to make sure that I'm absolutely not putting any pixels outside of the visible area. And then here I have the sync pulse. This is the timing that I can get from the timing here. So it's basically every time high, and then when I come in the sync range, I pull it low, and that tells the monitor that I'm outputting 1600 at 1200 at 50 hertz. So if you just use this, you have a black screen, and if you ask the monitor for information, it will display you that you are creating a 1600 times 1200 signal. So that was the generating, but now we need to decide what color each pixel has. And this is this loop. So let me clear this a little bit up. And let me open this one. So in my in the PowerPoint sheets, I told you that it's not possible to display a whole image because I simply do not have enough block RAM to store the image. So this means I need to do clever things to save block RAM. And one thing that I do is just store little parts of the image that I want to display, so I can save space. So if you, for instance, look here, the VI Technologies logo is a color logo. So every pixel has 3 bits value, RGB, and I only store enough that I can display this logo. If you look at the astronaut and the text here, these are they are only black and white. So I can store this at 1 bit and need to do some clever wiring to make sure it's white or blue or whatever color I want. And using these techniques, I'm saving space, because this black area I do not have to save in block RAM because I'm simply not drawing anything here. These rectangles that you see down here are actually done programmatically. So I'm not saving anything in block RAM. I'm just asking, is the pixel that I'm currently updating inside or in range of this rectangle? If yes, then draw the color. And then the biggest part, of course, is the game itself, but we will come back to that later. So this is the 40 megahertz loop that tells the 160 megahertz loop which 4 pixels are we updating. Which means every iteration of this loop, we have to give out for the RGB values of 4 pixels. This VI is the same as the 2 counters we saw in the other loop, but because it's only a 40 megahertz loop, I can put the code somewhat more together. And in this cluster, I'm outputting the horizontal pixel and the vertical pixel that I'm currently updating. And each of these parallel VIs need to decide for themselves if the pixel that is currently updating is for them and what color it should have. For instance, if I have the astronaut VI, this is this one, it decides if the astronaut should be drawn. This is the position of the astronaut on the screen. So I first check if the pixel that is being drawn is inside this range. If so, I update a counter and read out my block RAM that has the information, that contains the information of the pixels that should be displayed on the screen. So how you do that is you create block memory in your project. So right click, new memory, and I have here the astronaut memory. It has a size, it has a name. What's important is that cycles of read latency is set to 1 because we are reading this in a single cycle time loop, and at default it's set to 2. But if I do this, it will not work. It will not compile because it needs 2 cycles to read instead of 1. It will ask you to pipeline the output, which is not visible in my VI here, but it is there. I can show that in just a moment. The data type is fixed point because each iteration of this loop I need to output 4 pixels. So I output 4 bits, which is my, and each bit is 1 pixel that I need to display. The interface are both read because I'm not writing to the block RAM, I'm just reading is only a ROM basically. And I have an initial values which contain the data, which contains the data of the astronaut. And to store this data, you have to make a VI that basically outputs the data of the astronaut. I can show you this. So this, these are my lookup tables that I use for the initial values of all the block memories. So I have one for the astronaut. If I run this, it basically loads an image, a simple PNG image, and formats it in a way that I can use it to store in the block memory as an initial value. I get extra information here, which you have to provide yourself, so you have to do some programming. But I load the PNG into memory. I have loops that will make sure that I put 4 pixels in one fixed point, and I output the initial data that is then stored into the block RAM. Yes. So another thing that I've shown was the rectangles, which are done programmatically. Those are these here, the draw rectangles. These just check again if the active pixel that is currently being drawn is inside a boundary. If so, then depending on the player, because I'm reusing this VI, I select the color. So this is red, this is green, blue, and magenta, and this is going on the output. So then there is additional logic here, which is very easy to explain, because if you, I'm drawing the astronaut here, but the game board is actually overlain, and this is an overlay, so the game board will always be drawn instead of the astronaut, and that's basically the logic that you can see here. Okay. I will come back for the Playfield because that one is more complicated, but the other parts of the display are all using the same kind of technique. So loading from block RAM is either 3 color or 1 color to save space, and you can basically define your display how you want. So now we're going back to the main VI. The last loop is the normal game loop. There it goes. Yes. So this is a state machine. This state machine runs the game for all 4 players. In this array of clusters, I have 4 states. So there are 4 elements. You can see here. But there are 4 elements, and each of the player has his own set of data. And what is happening is it will update the state for player 1. Then this VI will select player 2, and it will update the state for player 2. Then player 3, player 4, player 1, 2, 3, 4, 1. So this is how I also save space. I have one state machine for all 4 the players. Now, if I go to the documentation, I have, let me see, state diagram. So this is the state diagram that I'm using. Every state is one case in my case structure, and you can see the values that are needed for the transition. So we start the game, and we are waiting for the player to press the button on the joystick. So if the joystick button is true, it will initialize the game, which will reset the score, clear the board, etc. Then it will create the first tetromino, so the first Tetris block, and place it on the draw Playfield. I will come back for the differences between game and draw Playfield, but the draw Playfield is basically a part of the block RAM that is reserved, that is drawn on the screen. Then I will update the score, so the score on the display will be 0. Check of the game is game over, because the game over state is if I create a new tetromino and it is in collision with the stack, so the blocks that are already placed on the playfield, the game is over. It will freeze the game for a few seconds and then get up here where it is waiting again for the player to start the game. But if it's not game over, we check the drop timer, which is an internal timer that makes sure the block drops down after 1 second when the game starts. But if you start clearing more rows, it will go faster. If the drop timer did not elapse, it will check the joystick for input. If the user is doing nothing, it will check the timer again. It will basically wait here till something happens. Now, if the user does something with the joystick, it will first check if that what the user wants to do is a collision. So for instance, if you're on the left side of the screen and you want to go one block more left, so you basically are on the left border, it will not do that because you are in collision with the left border. So it will ignore your inputs and start the drop timer again, etc. But if there is no collision, so collision is false, it will move the Tetnomino to the new position, then do a copy. Okay, I need to explain the difference between the game and the draw playfield. So the game playfield basically only contains the stack, the blocks that are not falling down. And the draw playfield contains the stack and the block that is currently being used. So by copying the game to the draw, it basically removes the falling block. And now I place, so I go here, now I place the Tetnomino on the draw playfield, which makes it visible again. Then I update the score, and etc. etc. There are two cases, which is basically dropping the block onto the stack, which is placing the block, which is placing the block on the stack. So what we need to do here is check if we have any full lines, remove those lines. Then I added a check for a perfect clear. So if you clear the whole board, so there's nothing on it again, you get 20 extra points. Then I copy again the game to the draw playfield and create a new Tetnomino and etc. So this is the state machine, and the state machine is used here. So if you open or see the case selector, you can see all the cases that are visible in the state diagram. And every function is programmed here. I can maybe explain the block ROM a little bit better for this. So this is how the game is basically built up at the moment. Because an LabVIEW FPGA only supports 1D arrays and not 2D arrays, you basically have a long 1D array where you do all your manipulations on. So the game field is 10 by 20. So it's basically a 1D array from 0 to 199 elements. And I created a game playfield block RAM, which contains all the 4 game fields for each of the players. So this is player 1, and from 200 there's player 2, etc. And I created 4 single draw playfields, which are which is basically a copy of the game playfield plus the block that I'm currently using to draw it on screen. These are all the possible Tetrominos you can use, and all are built up out of 4 blocks. So I can store these offsets also in block memory. So if I have this block and I create an origin at 0, 0, I can store this block in memory as an offset of 10, 11, 12, and 13. So if this block would be located with an origin of 0, so here, and I add an offset of 10, the block would be actually visible at 10, 11, 12, and 13. And I can do that for all these blocks. This is also how I check collision, because if my origin of this block is at 0, it is actually on 10, 11, 12, and 13. So if I wanted to go left, I check the first, can I go left? No, because from 10 to 9 is not allowed. So I have a collision. I will actually also check if 11 to 10 is possible, 12, etc. But because one of the 4 blocks is in collision, the whole movement is ignored. Or if it was a movement down, it will be deployed and a new block will be created. Yes. So let me see. Yeah, so one thing that I'm using for creating a Tetnomino, I need a randomizer. And what I'm using here is the noise generator, which is a native function from LabVIEW FPGA toolkit. So if you're using LabVIEW FPGA, you can use this. I'm creating a random number from -4 to 3. I actually only have 7 determinants, so these are 8 possible combinations, so I need to ignore one. And I create a random seed by reading out the tick count, which the FPGA is currently on. The tick count is random because remember, we are iterating from player 1 to player 2 to player 3, and all of them are in a different state. There is actually a difference in when the users are using their joystick. So this is random, and it's so there are Tetris games which give you all blocks in the same amount, so they monitor how often you get a block type, so you will get all blocks at the same amount. This will not do this. This can do this. It can take a long time before you get the favorite long block that will save you in the game. So Maarten, are there any questions of parts of the code that people want to see or want to go in more detail in? Not yet. So what's the time? So I think I'm basically done with my presentation. So you can also download the source code for Tetris. It's in the description of the YouTube channel. It's free of use. You can do whatever you want with it. It should be relatively easy to port this to another Rio architecture, so a compact Rio of a PXI. What you need is at least 5 digital inputs for the joystick, for at least one joystick, and 5 digital outputs for the phaser signal, and then you can make this this running again. I can maybe show the joystick logic. Let me see. Check the uptime, data collision. Oh, it's here. Yeah, I combined 2 states here because the wait state is waiting for a button down, and the check joystick is waiting for any joystick. And to save resources, I put them in the same case because the digital inputs here will be compiled only one time. So again, when I was compiling this, and maybe I could show this. Show district compilation zones. I hope it will show it. Yes, it will still show it. If you look at the final utilization, I'm at 100% of slices. Slices consist of registers and lookup tables, but if you look at these 2 resources, I'm only using 35% of the registers and 48%, 85% of the lookup tables. So it's not, there is still room, but I have difficulties getting this to compile. The block RAMs, I only using 65%, so I can do much more here. And the DSPs, which are multiplications, I try to minimize from the start, so only using 7 of the 80 that I'm having. But because I was having difficulties getting this compiled, I have created one VI for all the 4 joysticks, and I have a case structure depending on the player who needs to have their input read to select the digital I/O. So I have 5 digital inputs for joystick 1. Then I have a inverter because it's a pull down, no, pull up resistor. So if nothing happens, the inputs are high. If the joystick is moved, the input that is directly connected to that move gets set to 0 or to false, so I need to invert it. Then I have a debounce function. Yeah, and then depending on the input, I will output it. And then the next input that I need to have is a none. So if I do a direction on the joystick, the next input this VI wants to have is a none. So you have to release the joystick and get it back to a neutral state before you can do the next input. This gives you extreme precision when controlling the blocks, because if you do one time left, the block will go one block left and not more than that. I have to release the joystick, or yeah, release the joystick, and then I can do the next one, and that works very well. I'm still having troubles with the debounce values. As you can see, I'm waiting for 20,000 ticks. So this is a single cycle time loop at 40 megahertz. So this is 20,000 times 25 nanoseconds, which is still too fast. I think I need to basically add a 0 here, add a 0 in the timeout of this loop, and then we will not have any debounce issues in the joysticks again. And yeah, we will be displaying this on the next NI days, NI weeks, whatever will be next, depending on the current situation. But if you see this, please come to us, play. We will have an amazing prize for the yeah, for the people that will get the highest score. And I think I'm at the end of my presentation. Are there any questions? I see one question. So you already programmed Snake and Tetris. Do you have concrete ideas about which games to program next? Yeah, so I want to always increase the stakes. I'm working on one project which I'm not ready to announce yet, but I already ordered light guns. So the NES, if you know the NES game, the Duck Hunt gun, you can actually not use the guns that were delivered with the Nintendo Entertainment System, because it compensates for the CRT scan that monitors in that time had. So if you will use the light gun on an LCD, it will actually detect nothing, and it will not work. So a light gun, if you press the trigger, it will send a digital pulse, and the screen will go black, and there will be a white square, and the gun will actually look for that square. If it detects it, you basically hit your target, and you get another signal back from the gun. If you miss it, the gun will just not reply, and you know you missed. I'm still looking what game exactly to make. Duck Hunt would be obvious, but there are a lot of other possibilities. But that will be a long time out, if even I will ever do it. If you go to the Snake blog, so in the description, and if you go to the VR Technologies website, go to the blog and then Snake on FPGA, you will find the VIs that are needed for just generating an 800 by 600 signal, and you can concentrate on the logic for whatever you want to display. I'm also looking into a library where you can visualize the voltage measured on an analog input, for instance, or monitor the digital outputs. So you can use this library to in your real time in your projects to debug the FPGA without influencing the RT or setting up a data stream or whatever. So you only need at least 3 digital outputs, so the horizontal sync, the vertical sync, and 1 pixel color, and you can wire it on the connector to either be it black and white or black and red or whatever you want. And then you can display the actual voltage that is measured on a digital, on an analog input of the FPGA. So you get some kind of feedback. Okay, so I think we have come to the end of this. Thank you, everyone, for viewing our first online DutLUG meeting. I hope we will do more of these. Keep viewing your social media post for more information. And if you have any questions, please mail them to us. All the slides, all the information that you have seen during these 3 presentations will be in the description of this YouTube video. It will also be on the DutLUG community thread. Find your own user group. It's very important for your own career, for your own understanding for LabVIEW, and it will make your life better, because every one of us has been struggling with solving some code, and what is hard for you is maybe very easy for somebody else. You can give you one tip, one VI, and you're happy again. So yeah. Okay. Thank you very much, everyone, and maybe see you next time. Bye.